Alright, we're going to go through the P11 Equilibria homework. So question 1a, there are several stages in the industrial production of methanol from methane. The first stage involves a gaseous equilibrium between the reactants, so methane and steam, and some gaseous products. Figures 1 and 2 show the percentage conversion of methane into the gaseous products under different conditions at equilibrium. So we've got two graphs here, so I've just kind of simplified it. So we can see that we've got temperature and the percentage conversion of methane at a constant pressure. So when we increase the temperature, the percentage conversion of methane is increasing up to a point, okay? And that's quite important when it comes to explaining how you're deducing the optimum conditions. What we can see with pressure is the percentage conversion of methane decreases as the pressure increases. So this is a levelled question. So it's a 6 marker, which means you're going to have 3 stages that you need to hit in terms of the chemistry content. So for the first stage, they're looking at what deductions you've actually made from the graph. So mark 1A is for stating, so 1A, the yield increases as temperature increases. Okay. However, at a certain point, so that's 1B, okay, after, and specifically what temperature is that? I'd say after around 880, it plateaus. So after 880 degrees, there is no increase any further. So that's 1B. 1C, looking at the pressure graph, the yield decreases as pressure increases. So these are your 3 marks then for stage 1. A statement that the yield increases as the temperature increases, but only up to a certain point. So you're saying that it plateaus. You can look specifically at what the temperature is on that. I think it's about 880. So after 880, there is no increase. And then we're looking at the second graph here. So the yield decreases as pressure increases. Okay. Stage 2 then is how you actually decided what your optimum temperature was. So for 2A, you need to state that it's how we come to a compromise. So even though high temperatures are increasing the yield of the reaction, high temperatures are expensive. They're expensive to generate. The equipment to withstand high temperatures is expensive as well. The other thing then is there's no point in having a really high temperature, because after we said it was around 880, it plateaus. There's no longer an increase. So point 2B was for stating the yield no longer increases. So there's no gain in using a higher temp. And then the final mark for that, so 2C, is for actually stating what your optimum temperature would be. So anything between 780 and 880 is what they've given on the mark scheme. Okay, so it was for some type of estimate. You had to actually say, I'm going to choose the optimum temperature of about 780, because there's no point after 880, the yield is no longer increases. Okay, for the last stage then, stage 3, you have to decide what your optimum pressure is and explain why. So 3A is for stacing. What we can see here is that as the pressure is increasing, the percentage conversion of methane decreases. So really, a low pressure is going to be the best that we need. However, there's a problem with having too low a pressure. So 3A is for saying a low pressure will lead to a low or slow rate of reaction. 3B, so a compromise is reached. And generally, when we look at the pressure, it almost kind of the percentage conversion decreases. So there's no point using a high pressure of above 3000. So here, they said the optimum pressure would be between 1000 to 2000 kilopascals. Okay, so the idea is that really we would want as low a pressure as possible. However, you have to take into account that there will be a very, very slow rate of reaction. So that's why you have to compromise. You have to increase the pressure slightly. Okay, so when you have a look at the mark scheme, you'll be able to see the levels that were being awarded. So you need to work out how many points of each stage did you actually write down, and then award yourself either level 1, level 2 or level 3 for your answer. Okay, question 2. Hydrogen can be manufactured by the reaction of methane with steam. An equilibrium is established as shown by the equation. So use Le Chatelier's principle to predict the effect on the equilibrium yield of hydrogen if the overall pressure is increased. So when a question is asking about pressure, you've got to work out the number of moles on both sides. So on the left-hand side, we have 2, and on the right-hand side, we have 4. So when you increase the pressure, equilibrium is always going to shift to the side with fewer moles. So that's going to go towards the left-hand side. So if we're moving away from the product and we're moving away from the hydrogen, that means that our yield of hydrogen is going to decrease. So mark 1, what is the effect on the yield? The yield is going to decrease. And then your explanation as to why the equilibrium shifts to the left-hand side as there are fewer moles. And then the second mark, why is it shifting that way? To decrease the pressure, or to oppose the increase in pressure. You can't get the mark just to say oppose the change. That's too vague. You need to be more specific. Okay, 2B then asks, explain why the equilibrium yield of hydrogen is unchanged if a catalyst is used in the reaction. So what actually happens is a reaction at equilibrium, we've got a forward reaction and a backward reaction happening. And if we have a catalyst, it's going to increase the rate of the forward and backward reactions equally. So therefore, you're not going to get any change in the amount of hydrogen that is actually produced in the reaction. All that a catalyst does is decrease the time it takes to get to equilibrium. So mark 1, a catalyst speeds up the rate of the forward and backward reaction. Mark 2 by the same amount or equally. Okay, question 3. Dodecane is a hydrocarbon found in the naphtha fraction of crude oil. Dodecane can be used as a starting material to produce a wide variety of useful products. The scheme below shows how one such product, polymer Y, can be produced from dodecane. So name the homologous series that both C2H4 and C4H8 belong to. So C2H4 and C4H8, they both have the general formulas CnH2n, So the homologous series that they both belong to is going to be an alkene. Okay, so you needed to write alkene. Draw a functional group isomer of C4H8 that does not belong to this homologous series. So alkenes are functional group isomers of cycloalkenes. So a functional group isomer of C4H8, you can have two options. It doesn't say whether to do the displayed or the, well, you're going to have to do it as displayed actually. You could do it as skeletal. So we could have cyclobutane. Okay. Also, okay, you could have methyl cyclopropane. One, two, 4, 5, 6, 7, 8. So you could have had either this or this. It had to be a cyclic molecule. You couldn't have drawn another alkene because if it's a functional group isomer, it's changing the functionality. It's no longer got a double bond. It's going to be fully saturated. Okay, from the first part of the question then, it gave you a cracking equation. So we had C12H26 producing C2H4 and C4H8 plus molecule X. So part B, it says identify compound X. Very simply, you just need to take 2 plus 4 from 12, which is going to leave us with 6 carbons, and then 4 plus 8, which is 12, taken away from 26 will leave us with 14 carbons. So, or 14 hydrogen, sorry. So this is actually the formula for hexane. Okay, so that was the identity of X. Name polymer Y. So polymer Y has been formed from N molecules of C4H8. So that molecule here. Now, in this example, this would have been the starting structure. And the reason I know this is because of the actual polymer that's been produced. So when this polymerizes, that double bond has now been broken and we have a CH3 group on either side, which means the double bond would have had to be in the middle of the compound. Now, because it's an unsymmetrical, so the structure that would have been formed from, or would have formed this, is but2ene. So our polymer name will be polybut2ene. Not just polybutene, because you need to show that the double bond was actually between the second and third carbon. Okay. State one other condition that's needed for reaction 1. So it's an example of thermal cracking. It's carried out at a temperature of 750 degrees. So we need a high pressure. That's all that you need for that answer, high pressure. Okay, reaction 2 is exothermic. So reaction 2 is our polymerization reaction. A typical compromised temperature of 200 degrees is used industrially for this reaction. Explain the effect of a change in temperature on both the position of the equilibrium and the rate of reaction, and justify why a compromised temperature is used industrially. So this is actually linking kinetics and equilibria. So if they've told you that C4H8 polymerizing to give our polymer of polybut2ene. This is an exothermic reaction. So that means the forward reaction is exothermic, the backward reaction is endothermic. So it's asking you to explain the compromise between the effective temperature on the equilibrium and the rate. So for this question, it wants you to basically state that point 1, at a higher temperature, so if we increase the temperature, equilibrium is going to shift to the endothermic direction. Okay, so at a high temperature, equilibrium shifts in the endothermic direction. You then make it specific to this example, which is the left-hand side. Why does it do this? It shifts to absorb the added heat. Therefore, if it's going to the left-hand side, yield decreases. Okay, so basically you're kind of pointing out here that a higher temperature would give us a low yield, which isn't very good. So to increase the yield, we would need a really low temperature. And what they've said in the mark scheme is you could have written vice versa. You could have said at a low temperature, equilibrium shifts in the x direction, which in this case is to the right-hand side. It shifts to release heat, and therefore the yield would increase. But it then's asking you to look at the rate of reaction as well. So the reason why we have to reach a compromise, even though a high temperature leads to a low yield, a high temperature increases the number of particles with energy greater than or equal to the activation energy. Therefore, we have an increase in successful collisions. So the rate increases at a higher temperature. So we've talked about equilibrium, we've talked about rate. So then the last little section then is going to be looking at the compromise. So the compromise temperature is reached to balance yield, rate, and cost as well, because there's only so much that we can increase the rate of reaction by increasing the temperature before it gets too expensive. Okay, so the next question then, question 4, is a multiple choice question. So we've got C2H4 plus H2O produces C2H5OH. So this is the production of ethanol, okay, so by direct hydration. So this has an enthalpy change of minus 46 kilojoules per mole. So that tells us the forward reaction is exothermic, the backward reaction is endo. So question 4, which statement is not correct about the industrial preparation of ethanol by the hydration of ethene at 300 degrees? The reaction is catalyzed by an acid, so hydration has to occur with a concentrated phosphoric acid or sulfuric acid catalyst. So that is correct for A. The higher the pressure, the higher the equilibrium yield of ethanol. So we've got 2 moles on the left and 1 on the right. If we increase the pressure, it's going to shift to the side with fewer moles, so it is going to go that way. So B is also correct. The higher the temperature, the higher the equilibrium yield of ethanol. Now, if we increase the temperature, it always shifts in the endo direction, and in this reaction, that's the left-hand side. So the statement which was not correct was C. Okay, multiple choice question 5. For this reaction at equilibrium, which combination of temperature and pressure would give the greatest yield of the products? So the enthalpy change for this is plus 47, so that means the forward reaction is endo and the backward reaction is exo. So if the forward reaction is endothermic, if we want to get as much Y and Z, we need to have a high temperature. Okay, because if you have a high temperature, if you increase the temperature, it's going to shift it in the endo direction. So if we want more of Y and Z, we need to increase the temperature. Now, in terms of pressure, we've got 2 moles on the left and 3 moles on the right. If we want to push the equilibrium towards the side with more moles or more particles, we're going to need to decrease the pressure. So a low pressure. So which of our options then has low pressure and high temperature? The answer is C. Okay, so multiple choice question 6. A pale brown mixture of NO2 and N2O4 is allowed to reach equilibrium in a sealed gas syringe according to the following equation. When the plunger is pushed further into the syringe, the pressure increases and the mixture becomes paler in colour. When the syringe is placed in a hot oven, the mixture becomes darker in colour. Which of the following statements is correct? So what we've got here in this question, we know we've got 2 moles on the left and 1 mole on the right. So when the plunger is pushed further and we have an increase in the temperature, or increase in the pressure, we know the equilibrium is going to shift to the side with fewer moles. If you increase the pressure, it shifts to the side with fewer moles. So it's going to be going in this direction. And when they increased the pressure, it became paler. Okay, we know it's becoming paler because the equilibrium is shifting towards the side. We know that this is the pale one, because the equilibrium is shifting to the side with fewer moles, which is this side, which means the N2O4 is pale. When the syringe is placed in a hot oven, the mixture becomes darker in colour. Now, if we've just worked out that this is pale, then it means that this would have been the brown reagent or compound in the reaction. And so when the syringe is placed in a hot oven, if you're increasing the temperature and it's shifting that way, that means that that would have been the endo direction. So this would have been the exo direction. So which of the following is correct? So we know that NO2 is brown and the forward reaction is exothermic. So the answer, NO2 is brown, the forward reaction is exothermic, so the answer is A.